Okay, so we need to talk about stacks today. So stacks is a stack is a container, just like we've talked about. What are some of the STL containers we've talked about? STL, Standard Template Library. Vector. Bag actually isn't one. Bag is an example from the book. But a bag is like one of the containers from the STL. Yes. Deck is another one we talked about a little bit. Okay, there's a set, and there's a multi-set, and the bag is really sort of like a multi-set. Not exactly, but sort of. And then there were two others actually that we talked about last time in class that you haven't mentioned yet. Well, actually, I guess vector was one of them, huh? Was vector one of them? Yeah, vector was one, and the other option besides vector was list, right? And we talked about how vector and list were kind of the same, except vector was more like an array and list is more like a linked list. Okay, so stack is just another one of those. It's another container class that it's a well-known data structure in theory of computer science, but it's also a class in the Standard Template Library. Here's how a stack works. A stack is actually just like some other data structures. List comes to mind, except you can only add and remove things from one end. Okay, so can you imagine why they call that a stack? Like imagine you've got a stack of papers sitting on your desk. Okay, the analogy breaks down a little bit, but the idea is that normally what you would do is you would take the top piece of paper off first before you got down to the next one, right? That kind of thing. And then when you put things on the stack, you put them on the top. You don't slide them underneath, typically, right? So that's why it's called a stack. So really, it's basically like some other container classes that we've seen, except it's more limited, right? There's fewer things you can do with it. But it works very nicely for some situations. For example, we've talked about one situation a lot where it is used. Right? We talked about the stack is where we store automatic variables, local variables, in C++. Right? We've got the stack. And I don't know, I guess you may not have ever talked very much about the stack before. We'll be talking about it more, how it works. We'll be talking about how it works more when we get to recursion. But basically the idea is every time you have a function call, you put all of the variables for that function on top of the stack. And then when you finish the function, you take it back off the stack. So that what's left at the top of the stack is whatever the variables were for the function that called it. Okay, so you can go, one function calls another one, calls another one, calls another one. You can build up the stack like that and then bring it back down. So actually, there's probably not a good name for that. Line, I guess we call it. I want to start by trying to do a simple example of how you might use a stack. Okay, and I'm taking this pretty much straight out of the text. What I want to do let's see, let me and I'm also going to need to say # include stack. Okay, every time you use a container from the STL, you have to include the file that the corresponding file. Okay, I'm going to say int main if is balanced, and then I'm going to give it a string, and I'm just going to put in a string with a bunch of parentheses in it. And what I'm going to do later is I'm going to write a function to see whether or not those parentheses are balanced. Okay. So actually, before I dive in, can you tell me how that's going to work? How am I going to use a stack to do that? To check to see whether a string of parentheses is balanced. You know what I mean by balanced? Like
each one has an end and beginning.
Yeah, each one has a beginning and an end, so it would be valid in an expression. Any idea how I might use a stack to do that?
Well, you said how we can only take from one end, not the other. Right. That's the purpose of a stack.
Right.
So I guess if you had, let's just say you had 10 parentheses in there, like so there should be 5 groups of them.
Okay.
But let's say instead of 10, you have 9. So I guess you just go from the very top and you just see if there are. It counts the first number, like the first half of them, and it counts the other end. And let's say there's 4 on the front instead. Let's say there's 4 on the front and 5 on the back, then you know it's not balanced. Okay. But if it counts 6 and 5, it's still not balanced. But if it counts 5 first and then 5 on the other, it's balanced. So maybe you have a point where you can show that you can look at one type of parentheses, like the beginning of the one, and then it should be able to check for the end ones, like the 2 different parts, not just they look at parentheses. Period.
Okay.
I would just get a count and do modulus 2, and if you get anything other than 0, then it's not balanced.
Okay, so let's say.
That's like 2-minute thing there. Yeah, that works.
Let's say here's the string. Okay. Is that balanced?
No.
So I think what you just said would have given an answer true for this, right? Unless I misunderstood. Okay. Yeah?
Are you thinking whenever you encounter an open parent, push it onto the stack, and then pop one off whenever you encounter a closed parent?
Yes.
And then when you're done parsing the stuff on the stack, you put it on balance?
Yeah, there may be a little more to it than that, but that's the basic idea. Every time you see an open parent, you're going to push it onto the stack. That's the word we use instead of put. Okay, push it onto the stack.
Okay.
And then every time we see a closed paren, we're going to pop something off the stack. Pop that open paren that we had pushed on the stack, pop it off the stack. If we see a closed paren and there's nothing on the stack, then we immediately know something's wrong, right? Because there's been more closed parens than there have been open parens. Any other situation where we know we failed? Well, actually, I guess you said it. When we get to the end of the string, there's still stuff on the stack. That would mean there were too many open parens, right? I'm thinking that you could also fail. No, I guess that those are the only 2 ways you could fail, I think. Because the first one will tell you if you have too many closed parens. The second one will tell you if you have too many open parens. But yeah, I think that's it. Go ahead.
So are we assuming that this string is a group of open parens and then a group of closed parens?
No.
Not mixed around?
It could be mixed around.
Well, if it's mixed around, then you can't, like if there's nothing on your stack and you come to a closed paren, then you can't just assume that it's unbalanced at that point because later in the string it could become balanced.
Well, I think that,
In a string. Yeah.
so like this. Okay, so at this point here, and say there's more stuff in the string, but I don't know what it is. I don't think that can be a valid. I don't think that can be. So when we say balance, we don't just mean the same number of open parens as there are closed parens. We mean that every open paren has a matching closed paren.
Like in English.
Like in English.
You like math,
You can math, you mean? Yep. Yeah.
Yeah.
Look at that.
Don't worry, it's like 8:45.
Yeah. So just like in mathematics, it's kind of like making sure you've got a big complicated expression with a bunch of parens and stuff, and
Start with a closed.
except the difference between this and analyzing a big huge expression is we're just leaving out the variables and the numbers and stuff and just looking at the parens.
Well, wait, is there a way that you could like make a difference, like when you write the function, make a difference between an open paren and a closed paren? Like make sure that every time the first parenthesis that you look at is always open, and then I don't know, just be able to have the function be able to differentiate between the two to make sure that they all match in the places.
That's what we're trying to do. Did you have something to say? Okay.
Sorry, I'm just stating the obvious.
Yeah, that's what we're trying to do. So let me see if everyone's with me now. I'll just say it one more time what our algorithm is going to be here. Okay. We're going to look at whatever the next character is in the string. If it's an open paren, we're going to push it on the stack. If it's a closed paren, we're going to pop something off of the stack. If we see a closed paren and the stack is empty, then we fail. And if we get to the end of the string and there's still stuff on the stack, we fail. Okay? So if I had something like that, I'm probably getting to the point where you can't really see it. So basically, these are balanced, and then I've got one extra. My algorithm will work on that, right? I'll push open paren, and then I'll push a second open paren, and then I pop the second paren off, so now I have one paren on the stack. And then I push one, so now I have two on the stack. And then I pop one, so now I've got one on the stack, and then I pop another one, so now I have none on the stack. And then if I try to do another closed paren, I fail. Okay? All right, so let's see if we can actually put that to code. So obviously if is balanced, and then just, give it a... Why did that go to the next one? Actually, you know what I should do? Okay, and then to take that a step further, let's Okay, so now we have a little driver that we can use to test our isBalanced function that we're about to write. IsBalanced is going to return true or false. So let's write isBalanced. Let me do the prototype while I'm up here. Cool.
You still have to declare a string.
Yeah. Oops. And I should also include string. Okay. We need a counter that's going to go through the string, right? So int count gets 0. Let me just use I. Int I gets 0. While so here's what's going on in my brain. I'm looking at the text and I'm saying, why did he do that? That doesn't seem, I mean, it seems like it'll work, but it seems like a really hard way to do it. So I'm trying to decide whether to just try going out on my own or whether I should stick with what's here because I know it works. But I'm going to try going out on my own here. We'll see if it works. So basically we want to say while I is less than my string dot length. Okay, and I'm thinking that if we get to a point where we see a closed paren and there's nothing on the stack, we can just immediately say return false, right? Okay, so what do we want to do? Tell me just in English. Don't tell me anything about C++ at all. Just tell me in English. What do we want to do right now?
The first character of my string.
Do what with the first character?
Like, read it.
Read it. Okay. Okay, and then do what with it?
Compare it to see if it's a closed or open paren.
Okay. Look to see whether it's a closed paren or an open paren. And if it's an open paren, we push it on the stack. If it's a closed paren, we...
At this point, we would have to delete.
Well, but I mean in the general case, right? Not just the first time through, but in general. Pop it. If there's something on the stack, we would pop it, right?
Yeah.
If there's nothing on the stack, then we would return false. Yeah.
What happens if you pop it into stack?
I'm not sure. Pop an empty stack. I think it'll stop execution. Like it'll crash. Pretty sure that's right. We'll try. So. I need a stack, so I'm going to say stack, my stack, int, because it's, no, car, huh? Because it's a stack of characters. Whoa. Okay, I knew I should have had my coffee this morning. Thank you. Can you just come up here and type for me? All right, I think I got rid of most of the squigglies. Okay, so as long as I is less than my string.length, we're going to say, so the easy part is if it's a left paren, right? If it's a left paren, we always just push it. So if my string sub I equals left paren. So something, sorry, little digression here. In the text, in this example, he actually creates a character named left parenthesis, a constant left parenthesis, and a constant named right parenthesis. And I don't really get how that's useful, personally, yes.
Could it be encoding? I mean, would there be something weird with that?
Encoding?
In terms of the character encoding, would that change anything, or
I don't.
C++ do that for you?
C++ will do all that for you, yeah. The only thing I can imagine is that he would argue that it's easier to read the words left parenthesis than it is to look at a left paren and know that there's a left paren, but I don't think that works for me. Anyway. Well, I guess that's what I'm saying. I'm not, for me, I'm not sure it really is more clear, but we'll leave that for the philosophers, I guess. Okay, so if my string sub I is equal to open paren, we want to say my stack dot push I guess we could just hard code it in there. Right? Okay. Else
At the end of the push.
Oh my, okay. Thank you. Okay, so now, so I guess, so now here's what's going through my brain. I'm trying to think, what do we do if we see something that's not an open paren and not a closed paren? And I guess I would say let's just ignore it. Okay, so I'm going to say else if my string sub I equals closed paren, then what do we do?
Should we check to make sure there's something on the stack first?
Mm-hmm. Yeah, I can't just say pop right here because it might be easy, right?
Should you put that into that slot?
Okay, there's a couple of different ways of doing it. I could say right here, I could say if my string sub I equals close paren and the stack isn't empty. And then I would have a final else that would say if it's equal to a closed paren and the stack is empty. I kind of like it. I'm going to do it a slightly different way. Okay, I'm going to try nesting it instead. Okay, so what I'm going to do here. What it goes in here is all of the code that processes the case where my string sub I was a closed paren, right? So if my string is a closed paren, what do we need to do? If my stack dot empty return false, right? Everyone with me? Else pop it actually. We're at the close point. So stack dot pop. Yes. Okay, and then so now I get to the end of my while loop. So at this point, I know one of two things is true, right? Either the stack is empty or it's not. So if stack.empty my stack. Return true. Oh, actually, hold on. Else return false.
Under the while, the function will increase I.
Oh yes, inside the while loop at the bottom. Yeah, thank you. Yeah, so everyone look at this. This is actually in the style conventions, right? Okay. No, never need to say that. I can just say return my stack.empty. What do you think? So we give it a try. Let's do open, open, close, open, close, close. Balanced. Open, open, close, close, close. Not balanced. Open, open, close, close, open, open, close. Okay, that's not balanced. Up to the last three characters, right when you get up to the point where you're about to get the third to the last character, stack will be empty, because that's a valid expression up to that point. And then I'm putting two opens and one close. So basically I'm seeing if it works when I've got too many opens. Okay? I think we're in pretty good shape. Right, I know, I'm just saying, I'm just trying to see what would happen if I just used the empty string. Because it should.
So you want to check it with the other?
Oh no, I know the problem is. We use cn to read the string, and cn skips leading spaces, so it's not. I'm still working on the cn, so that's okay. I could use getLine instead, I suppose. So let's try quit. Okay? Any questions about this function is balanced?
Don't you want to check it with other characters and the string?
Oh, to see what happens? Yeah, good idea. So basically it's going to ignore other characters, right? So A, open paren, close paren, let's do another open. Open, close, open, close, close. Okay? Good. All right. Interesting, I was not planning on changing the example that he gives in the text very much, but I ended up doing it pretty much completely differently. So I'll have to post this and you guys can compare this with what's in the text and decide what you like better. Okay, so how do you suppose we should implement a stack? So this is kind of a pattern that he uses in the text, and also that I, to the extent that I remember, try to follow, which is first I show you the client program, because that tells you how I'm expecting to be able to use this thing that we're creating. Okay, and then the next step is to, well, I suppose the next, really the next step would be to look at the specification, the header file. But I'm going to kind of skip over that because we know there's going to be a push function, we know there's going to be a pop function, we know there's going to be an empty function. Those are the only three things we used, right? Okay. The only other one that's really obvious that's not here, or really, used a lot that's not here, is there's a function called top, which returns the first item on the stack, but doesn't pop it off the stack. Does that make sense? Okay. So let's go to the last step, which is we're talking about how we're going to implement a stack. Any suggestions?
Linked list.
Okay, that's a good idea. Why does linked list come to mind?
Because, like, with a singular linked list, you only really have easy access to the top, the most recently added pointer.
Right. So a linked list comes to mind very rapidly because it kind of fits the model of a stack pretty well. A linked list, it's very difficult to add and remove things in the middle. It's very easy to do it at the front of the list. Okay. Could you do it? Could you use an array to do this? Okay. So on a stack, it's easy to imagine, right? You would just, every time you push it, you just insert something at the front of the linked list, and every time you pop it, you just remove the front thing at the front of the linked list, and then to test to see whether it's empty or not, you just check to see whether it's null, right? Okay. How about with an array? Could you implement a stack using an array?
You have to move everything.
You'd have to keep shifting a lot of things.
You probably put it at the end, and then have some kind of index that is the last index, and then just increment that as you call stuff out.
Right, so it actually doesn't turn out to be all that bad. If you think of the top of the stack being towards the end of the array. So the array sub 0 is the bottom of the stack, and then you just keep an index that points to the top of the stack. So if I have 3 items in my stack, the bottom item will be an array sub 0, the next item will be an array sub 1, the next item will be an array sub 2, and then my index of top will be equal to 2. And then if I add something, I just add 1 to my index of top and put it there. Then to pop something, it's even easier. To pop something, I just subtract 1 from the index of my top, and I'm done. Okay, so the implementation of the stack is very simple. It's kind of nice, and so we will. I'm not going to dive into that right now because it's almost time to go to lab. I will just say that for chapter 7 in the text, what I'm thinking, never mind, I'm not going to say that. I guess I would just say I'm debating about how much detail to go into in section 7.4. So if you're one of those students who likes to read ahead, we're going to cover 7.4 pretty lightly. It's called pretty lightly. It's called more complex stack applications. I don't know. It's about postfix notation and prefix notation and infix notation, and that's actually pretty important. You know, as computer scientists, you should know about that. So the bottom line is, I'm not quite sure yet. I'll have to think about that one. Okay. So I will see you in lab in about 10 minutes. Oh, by the way, hold on.